Okay, so the phase model, and here it is in its general form, describes complex systems such as, for example, this fast spiking neuron that has many state variables by just one state variable, namely its instantaneous phase theta. So the rate of change of this phase of an oscillator I can be described as its intrinsic frequency, so the one that is produced by this oscillator oscillating itself, plus the sum of the interactions with all other oscillators in this network. And this interaction, gamma here, depends on the specifics of the model that you're investigating. Now, it has been quite useful to replace this interaction function with a sine curve, which results in the quite famous Kuramoto model. And additionally, we get a coupling strength parameter that scales the interactions. And this model has been used throughout the sciences to explain multiple phenomena, and especially synchrony. For example, in the flashes of fireflies, or as in this example, which I think you have seen in Micha's presentation before, where the person initializes these metronomes at random phases, and they are coupled mechanically through the styrofoam board and the two cans below. And through this weakly coupling, they start synchronizing over time. So now they have almost achieved synchrony. And this phenomenon, for example, can be explained with a phase model such as the Kuramoto model. Now, let's get to the real question here. How are we modeling neural traveling waves? And this can easily be done in TVB. So here we set up a two-dimensional grid of these black circles. And each of these black circles can be a neural mass model. It can be as abstract as the Kuramoto model, or more biologically realistic, such as the Wilson-Cohen or the Janssen and Ritt model. But for the sake of the argument, and because we're working with phase oscillators, we're going to use the Kuramoto model here. So each of these black circles is a Kuramoto oscillator. And we want to connect them first with all-to-all connectivity, which is illustrated here for one region that connects to all the others. And just imagine that all the others also connect in turn to the rest of this two-dimensional sheet. Now, if you simulate this, and I create a simulation with an intrinsic frequency of 10 Hertz, and I initialize the phases at random at the beginning of the simulation. And this is what happens. So very quickly, the random phases synchronize and the entire sheet oscillates in synchrony. So obviously, this is not what we wanted. This is not the traveling wave we hoped for. But if you think about it, what we saw before is a recurrent network with its nearest neighbors. So this is what I implemented here. This time, each of the oscillators is connected to its nearest neighbors with the simplest form, the von Neumann connectivity. So each oscillator connected to its immediate neighbors. And let's see what happens if I simulate this model. So as you can see, there are a couple of clusters of synchrony emerging, and they propagate through the sheet. So indeed, we do get traveling waves in this two-dimensional model of neural tissue. And now you can see the waves quite clearly. Okay, so let's go one step back and look at something different. So again, we have all-to-all connectivity as indicated again for the single region, but this time we also use distance-dependent time delays. So this region affects the outside region, like at one of the corners, with a longer delay than regions that are closer to this region. And let's have a look at what effect this has on our model. And in fact, you see traveling waves emerging very quickly. So it looks like we have discovered another mechanism that can actually produce or allow the emergence of traveling waves in a system where we even have all-to-all connectivity. So we have now two mechanisms. One of them is nearest neighbor coupling. This one is distance-dependent time delays. So what happens if we combine the two in one model? Do they interfere with each other or not? And as you can see, even in this case, they produce clusters of synchronized activities. The area is partially synchronized and propagates through space. So with these mechanisms combined, we still get traveling waves. Now, if we turn to biology, what we usually see is a distance-dependent connection strength, and this has been replicated throughout different species, for mouse, Drosophila, macaque, and humans, for example. And you see as the distance between neurons or brain regions is increased, the connection strength decreases. And not only does the connection strength decrease with distance, but also the connection probability. So the further two brain regions are apart, the less likely they are connected. And to make our model a bit more realistic, we're going to use this distance dependency and produce a network as illustrated here for one region again. So this time we have distance dependent connection probability. So as you see, the further the regions are away from this region, the less likely they're connected. And the closer they are, the more likely they're connected. In addition to that, the strength decreases as if regions are far away, which is shown here in deep blue, and the connections are stronger if they are closer, if the regions are closer to each other, indicated here by yellow color. And on top of that, we have again distance-dependent time delays. And for this model, I also increased the spatial resolution. And this is what it looks like. So again, traveling waves emerge. In this case, we almost see rotating waves emerging. And yeah, so let's step this up one notch. And we basically use the same synthesized distance-dependent connectivity, this time in brain regions embedded in three-dimensional space. And here's what this looks like. So we're looking at more than 10,000 oscillators right now. And you can see pretty quickly from the random initial states, these 10,000 oscillators organize in a way to produce traveling waves. As you can see, they're large wavelength almost across the entire cortex and happily propagating through the brain network. Now, as you see, if you have empirically realistic distance-dependent connectivity that you would find empirically in the brain or in neural tissue, you already have the preconditions for traveling waves to emerge. So most of the time, if you use TVB and you use the structural connectivity, you already have the prerequisites for traveling waves to emerge. And many models can actually produce traveling waves. So in summary, we have seen what traveling waves are. We have seen what they look like in the brain. We have seen that they exist on a small scale, as in this case, or on a large scale, as in this case, which propagates almost through the entire cortex, or possibly even through the entire cortex. We have also seen that you can detect them in different modalities, from LFPs to EEG to a ball fMRI, also voltage-sensitive dye imaging, and so on and so forth. Then we have speculated and also talked about the functional significance of traveling waves. So they have been found to modulate neural responses, also to gate perception. They have been found to mediate information transfer, and possibly they play a role in memory processes. And then we have pursued the question of whether pathologies can affect cortical traveling waves, and indeed in the few studies that have investigated subject, they found that cortical traveling waves are indeed affected by various pathologies. Now, in the next part, we have looked at mechanisms that could underlie neural traveling waves. The first mechanism was delayed excitation, which results from a single exciting oscillator that excites other entities through increasing time delays. Then we have seen another mechanism of propagating pulses in an excitable network that basically propagates in a sort of a domino effect these entities, again via time delays. And the last one, and a very important one, phase locking in weakly coupled oscillators, where each entity is self-oscillating and they affect each other only weakly, so they do not distort their limit cycle, but only influence the timing within the limit cycle. And furthermore, we have computationally investigated mechanisms in weakly coupled oscillator model, and we found that in particular the connectivity, like nearest neighbor or distance dependent connectivity, is important for waves to emerge. We have also seen that time delays, distance dependent time delays, can achieve the same effect. And we also saw that realistic brain connectivity, which is distance dependent and has distance dependent time delays, also results in the emergence of traveling waves.